You know that feeling when your hard drive gets full, and now you have to start debating on which files to keep and which to delete? You might want to use Google Drive, Dropbox, or iCloud, but no. Today, I'm going to show you how to use YouTube to store your files. You might be asking why. Well, you can upload a ton of videos to YouTube, and each YouTube video can be up to 256 gigabytes or 12 hours, whichever limit you hit first. Instead of paying hundreds of dollars for, I don't know, iCloud, why not just capitalize on YouTube's file storage system? It should be easy, right? As long as we convert our file into a video we can upload? Well, the first thing we want to think about is how we're going to store our file data into a video container. When you look at any video file, you'll notice it ends with a .mp4, .mkv, .mov, or something similar. This is called a video container because it holds all the video, audio, and subtitle tracks that are needed for you to play the video. Things like authors, descriptions, and thumbnails can also live inside the container. Basically, it's just a portable bundle that media players know how to decode. And that leaves us with a lot of options for storing our file data. We could store it in the video, the audio, the subtitles, the metadata, and honestly anything. However, we actually can't use most of these options. If our end goal is storing files on YouTube, YouTube actually gets rid of most of these attributes when you upload a video. For example, metadata like the authors and description are stripped out of the file because they aren't relevant to YouTube. Subtitles aren't stripped out, but they could be rejected by YouTube if they are invalid or store too much data for the subtitle engine to process. That leaves us with two main options, video and audio. YouTube obviously conceptually keeps both of these tracks so that you're able to see and hear the video you're watching. And both are completely viable, but which one should we pick? Well, let's take an example. What is audio? Audio is made up of sound waves, and to represent them digitally, we take many samples and measure each signal's amplitude at a specific moment in time. During playback, speakers or headphones use these samples to reconstruct the waveform we perceive as sound. And some systems might use one channel, while others use two channels, allowing separate samples to play through the left and right ears. For example, a CD quality stereo audio sampled at 44,100 samples per second with 16 bits each sample requires about 1.4 megabits per second of data. Video, on the other hand, is stored in an array of pixels. For instance, a 1080p video is 1920 pixels wide and 1080 pixels tall, or around 2 million pixels in total. Each pixel, let's say, contains R, G, and B values that are 8 bits for each color channel or 24 bits in total. That means that each frame of a video is 48 million bits. And at a standard frame rate like 30 frames per second, this means that we are displaying over 1,500 megabits per second of data, which when uncompressed is over 1,000 times more data than audio. It's clear that video is the better option, but that doesn't rule out audio completely. We could theoretically use both at the same time, but the amount of data that video gives us completely dominates audio to the point where it's not even worth coordinating both at the same time. So for now, we're just going to stick with video to store our file data. From here on, it feels easy. Since our file is just bytes, we can encode those bytes directly into pixels. If we are using RGB, this means that we are using 3 bytes, one for R, one for G, and one for B. That way, we can split our file into 3 byte segments and just encode each pixel with our file data. But in reality, the situation is much different. Earlier, I said YouTube keeps the audio and video tracks conceptually. I assumed that meant it stored the exact file we uploaded, but that's not actually what happens. In order for YouTube to support everyone's massive uploads, they compress our videos. So when you upload a video, YouTube re-encodes it into different resolutions and formats, so it can stream efficiently on different devices and bandwidths. You may have seen this when the video quality gets lower when you have bad internet. There are many types of video compression, but the most important part of this is that YouTube's compression is lossy. So what does that mean? Well, it means that YouTube actually tampers with your video file data to save space. For example, small details in your videos might get removed, causing pixel colors and therefore their byte data to change. This causes the video you see to not be the identical video you uploaded. So this is where our plan starts to fall apart. Our approach only works if YouTube keeps our video data intact so we can recover it later, but YouTube re-encodes everything using lossy compression, which means parts of the original data are permanently discarded. And even worse, their compression algorithm isn't public, so we don't even know exactly what's being changed. It's like tossing our file into a black box and then getting back something that only somewhat resembles the original file. Now, this is where most people would give up. But I made you guys a promise, so quitting wasn't an option. If YouTube insists on recompressing everything we upload, then maybe the solution isn't to fight it, but instead design around it. So let's take a step back. Earlier, we were writing raw bytes directly into pixels, splitting the data into tiny 3-byte chunks. But that makes every small change from compression disastrous, because even a single corrupted pixel can destroy the data it carries. So instead of a singular pixel, let's think bigger. Instead of tiny pieces, what if we group the data into much larger sections, let's say like 1 megabyte blocks? Now, each big block becomes something we can protect and verify. But how can we protect and verify if each block is fine or not? To think about this, I like to bring up something surprisingly familiar. Something you have definitely seen before. From posters of lost pets to shipping products. Do you know what they are? QR codes aren't just black and white squares that you can scan. They're genius technology designed to survive damage. You can scratch them, smudge them, tear them, or even print them horribly like the diagrams on your exam, but they'd still work. So how's that even possible? Well, when you look at a QR code, they don't just store the raw data. They deliberately store extra data alongside it. These additional bytes act like built-in protection, which detects when part of the code has been damaged. They can also, in many cases, reconstruct what was lost even when parts are missing using an algorithm called Reed-Solomon. This entire process is called redundancy, which is something you see not just in computer science, but in aircrafts, power systems, and many other real-life applications. We can borrow that redundant design here. If we treat YouTube's compression as a noisy, lossy layer, like the QR codes subject to damage, then each block we store can have its own protection. But in order to do that, we would have to answer two main questions. 1. Has this block been corrupted by compression? And 2. If it has, do we still have enough redundant information to reconstruct the original data? We want to design our system to assume damage like QR codes, so it can be resilient to the video compression. Now you might be asking, why can't we use QR codes directly for each big block we are trying to keep error-prone? And your question would be valid. Why shouldn't we use something that has been proven to work millions of times in our video storage example? The truth is, QR codes are over-engineered for our specific video compression issue. They're subject to face different challenges like scratches and tears, which are things we wouldn't experience with YouTube's video compression. Also, encoding one QR code for every chunk of our file uses a lot of unnecessary storage, which doesn't make it an ideal way of storing our blocks. Let's go back to the drawing board and address each question with a different solution then. Our first question is how we can tell if a block has been corrupted by compression. Well, we've actually solved this problem before already, except in a different place. Network connections face this challenge on a daily basis. When you download documents, videos, or any file, your connection could be unreliable due to weather, outages, or anything to be honest. This could cause certain chunks of your file to be corrupted during transport. And to fix this, networks use something called a cyclic redundancy check, or CRC, to detect damaged chunks. CRC uses incredibly clever math to generate a fingerprint for every chunk of data. Under the hood, CRC treats your data like one long stream of bits and runs it through a special division process to generate a fingerprint. But this isn't normal division with subtraction and carries. Instead, everything happens in binary using XOR, which makes the math super fast for computers. You can think of it like feeding your data through a fixed pattern called a generator, and whatever remainder is left over from the division becomes the checksum. The remainder is strongly tied to the exact bits of our original data, so even the tiniest change completely alters the result. For example, suppose we want to send a chunk 1101. We pick a small generator pattern, which is basically a constant that determines how many CRC bits we want. And for simplicity, let's use 1011 as our generator pattern. First, we append a few zeros to the data so we can make space for our remainder. This gives us 1101,000. Then, we perform this XOR-based division, lining up the generator and XORing whatever the leading bit is 1, just like long division. After a few rounds of shifting and XORing, we're left with a small remainder, let's just say 001. That remainder becomes our CRC, so the value we actually transmit is 1101,001. When the receiver gets this, they perform the same division again. And let's see what happens if we do it on intact data. We get a remainder of 0. But now, let's change a singular bit and do the same division again. The remainder isn't 0 anymore, even when one value changed. This is the secret magic of CRC. Tiny changes in the data produce completely different fingerprints, so instead of checking every byte, we can get a super fast mathematical guarantee that the block is either intact or corrupted. But there's a catch. CRC isn't perfect. If the corruption itself happens to divide evenly by the generator number, it would give us a remainder of 0, which would give us the perception that the block is intact. In reality though, it's super rare, especially with a good CRC. In my project, I use CRC32 for my chunks for error detection, which for random corruption has a 1 in 2 to the power of 32 or 1 in 4.3 billion chance of being wrong. That's like picking one person out of half of Earth's population blindfolded and getting it right the first try. It's so small that it's essentially negligible for our use case. CRC is great at catching these errors, but it doesn't answer our second design question on whether or not we can reconstruct our original data if there is corruption. To solve this, we need another algorithm on top of CRC that's able to recover our data. There's many forward or error correction algorithms we could pick, like Raptor, Reed-Solomon, used by Curacode's LDPC, but I opted for using a library called Wirehair. I chose Wirehair because it scales really well for larger files. Behind the scenes, Wirehair uses something called a fountain code, which is basically when you break your data into small pieces and then generate extra repair chunks for each piece. Each repair chunk isn't a copy, but a smart bitwise mixing of the original chunks together. You can think of it like a system of equations. One chunk might represent A XOR C, another B XOR D, another A XOR B XOR D. On their own, they don't mean much, but altogether, they form a system of equations that you can solve. So if some chunks get lost or corrupted, which we expect after YouTube's video compression, we are able to solve and reconstruct our original data as long as we have enough total pieces. Now in reality, Wirehair is incredibly complex, and is filled with beautiful linear algebra proofs that allow it to be successful. I have attached Wirehair's repository below where you can see the code for reference if you'd like to dive deeper. Combining these two methods together, we're able to finally create a design that both checks for errors within each chunk and can recover if certain parts are lost after video compression. In my code, I use both of these algorithms alongside headers I've created to communicate information from the encoder to the decoder. However, this still doesn't explain how we actually store data inside a video in the first place, which turns out to be its own challenge. Previously, we used pixels to represent file data, but what can we do with the error-proof blocks when encoding them into the actual video file itself? Well, when encoding our video file with FFmpeg, we have to keep a few important things in mind. First, YouTube is going to recompress whatever we upload. And second, even though we don't know how YouTube compression works, we know that in general, video compression isn't random, and that most modern codecs don't operate on the raw pixels itself. For easier compression, they often transform each frame into the frequency domain by splitting each frame into smaller blocks, like 8x8 pixel squares, while trying to represent these squares using patterns. After transformation, low frequencies capture the broad shapes and lighting, while high frequencies capture tiny details and noise. This entire process is called a discrete cosine transform, or a DCT in signal processing. As for an example, let's take a look at this 8x8 block of pixels and one channel that are similar in color. After running a DCT, those pixels aren't stored directly anymore. Instead, they turn into frequency coefficients that might look something like this. That big number in the top left is the overall brightness of the block, and the small numbers nearby describe gradients. Everything else is tiny detail or noise. Video compression aggressively rounds away small details and noise and leaves the big number because those are what our eyes notice the most. Instead of hiding our data in fragile pixel values, we hide it directly inside those big coefficients in the top left, or the parts of the block that control the overall brightness and shapes, and the parts of the codec that's least likely to round down. We also should hide our bits into the signed bits of each value, since the magnitude itself will always change, but the sign has a greater chance of surviving. To do this, for each bit, we will gently push one slightly more positive or negative. When we push our coefficient a little farther away from 0, it has more breathing room. Even after compression squashes it, it usually just stays positive or negative. In other words, the magnitude changes, but the sign survives, and that's enough for us to reliably recover the bit. There's one more catch though, which is what video format we export our frames in. If we save the video using a lossy video codec like H.264 or AV1, we'd immediately lose precision because the codec itself already uses some level of video compression. This would mean we are effectively corrupting our data twice, once through export and again through when we upload our video onto YouTube, which goes through their compression algorithm. That's why we need to export the video using a lossless codec instead, preserving each pixel as close to the original as possible. That way, the only lossy step that ever touches our data is YouTube's recompression. Now that's all. There's only one thing left to do. Let's try it. Here I have my IDE here, and you can see my code. I'm going to compile it, and I'm going to go into my folder, and there's the tool I made for re-encoding and decoding the file. Right here I have an input.txt as an example. It's the B-movie script, and I'm going to run this command to first output it into a video file that we can upload onto YouTube. And I'm going to speed through this a bit because it takes a bit. And here now I'm going to upload my video onto YouTube, make it unlisted and do all the stuff, the logistics. I'm going to copy the link here. And then once we copy that link, we're going to use a tool called YTDLP, which is an awesome tool that allows us to download the best video quality from our YouTube link. So we're gonna run that command, format best video, and put in our URL there. It's gonna give us a new video, and notice how this video file below is much smaller, 1 megabyte versus 20 megabytes. I showed it what it looks like on screen. And then let's go back and use our same tool to decode the file, right, from whatever comes out of YouTube. And we're gonna output it with a different name because we don't want it to overwrite our test file control. I'm gonna speed this up a bit so that you guys are able to don't have to wait for this. And you can see that once we open our decoded file here and compare it with our contents of our original file, the control file, it's exactly the same. We got back the B movie script, we got back everything exactly the same. So yeah, that's how the tool works in action. There's honestly so much I learned throughout this entire research and coding process, and at first I didn't even think that this would be possible. Well, there you have it, file storage on YouTube. Is it ideal? Probably not. I mean, the extra file size you need from layers of error proofing is likely not worth the hassle, but it's cool seeing this working in principle. The code's open source, so you can view it in the GitHub link below. It's written in C++ and uses some libraries that you may have to install in order to compile it.